There we go. So when we get our triglycerides checked, we're checking the ratio between good and bad. And bad triglycerides are going to accumulate in areas like your blood vessels. And they create a dam, and then that can cause you to have big, big problems. So these triglycerides, they're called triglycerides because tri means what? 3. Glycerol. Triglycerides are 3 glycerol bonded together. These are also known as fatty acids. And I'm willing to bet, even though you don't know that you know, the 2 most common fatty acids are ones that you've probably heard of. Omega-3 and omega-6 fatty acids. Omega-6 is the kind that you have in your shampoo, in your creams, omega-6 infused fatty acids, because it helps with hair, skin, and nail health. Omega-3 is going to be more internal benefits. Now, we have a couple of different categories for our fats. And again, you've probably heard these terms. Saturated fats. Everybody's like, oh my God, stay away from saturated fats. Saturated fats, it doesn't necessarily mean they're super bad. What happens with saturated fats is saturated fat contains nothing but single bonds in that hydrocarbon chain. Saturated, single. So what we're looking at is just single bonds, nothing but single. But we know that these simple bonds are very easy for our body to break. And so I get a tremendous amount of energy. But if I'm taking in this much energy and I'm only needing this much, where does all the difference go? It goes to the storage unit, which is where? Everywhere. It's your adipose tissue. Unsaturated means that there is one double bond somewhere in the hydrocarbon chain. And where that double bond is going to determine what does your body do with it. Why is it called an omega-3 fatty acid? Why is it called an omega-6 fatty acid? Because that's the location of the first double bond. At the 3rd triglyceride or at the 6th triglyceride. And your body sees that double bond and it goes, okay, well, that one's at the 3rd. Here's what I need to do with it. And that determines what your body's going to do with that particular fat. Polyunsaturated would be more than one double bond. The more double bonds I have, the more energy I need to use to break them apart. Double bonds are harder to break than single bonds. The more double bonds I have, the more energy I'm using, the less energy I have available to go to the storage unit. When our triglycerides decompose or break apart, we call that hydrolysis. So hydro can mean either water or energy. What is lysis? To break apart. So those are just some very basic, very, very general facts about lipids. And they make stuff taste great. I had some delicious lipids last night. I live on those HEB Simple Meals. Oh my God, if you haven't tried them, they're fabulous. And I had, what did I have last night? Garlic, basil, chicken with mashed potatoes and green beans. Oh, it was delicious. It's like eating gourmet. Tonight I think I'm having flank steak with asparagus. I don't remember what I bought. So this is just a picture. Now, obviously, this is just a very, very basic picture. Here we've got our saturated fatty acids. We have nothing but single bonds in that hydrocarbon chain. And I know somebody is going to be like, but Miss Huff, there's a double bond right there. That's how you sound in my head sometimes. Okay, so yes, I agree with you. There is a double bond right there, but is this double bond in the hydrocarbon backbone? It is not. I am only looking at this hydrocarbon backbone. Here I have one double bond, so we would say it's unsaturated. Sometimes we'll say it's mono unsaturated. Although if you just say unsaturated, it's implied. If, erase. Let's say I put another double bond in here. Now what do I have? More than one, which would be the definition of many. Poly unsaturated. The word un means that there are double bonds. Poly unsaturated would be more than one double bond. All right, so the next category is our phospholipids. When we are really going to be talking about phospholipids, I think it's in the next chapter. We'll get that started probably tomorrow. We're going to be finishing up this chapter, although, hey, I'm going to give you guys a wee bit of a break. I'm not going to schedule a test over the weekend. We'll do it early next week sometime. I'm not going to do that. I give you guys a bit of a break. But phospholipids is a phosphorus and a fat. And where this is, where we're going to study is in the phospholipid bilayer or double layer of our cell membranes. I have here, you can see, here's one layer, here's two layers, and those are my phospholipid. This is also where we use the words hydrophilic. What is happening if you are hydrophilic? You love water. Hydrophobic, you are repelled by water. So in this phospholipid bilayer, why do we have this? So the bilayer, the skin, the cell membrane is really just like the skin of the cell. Your skin helps to prevent stuff from getting in, and it also helps to prevent stuff from getting out. That's the exact same thing that's happening with your cell membrane. I think of the cells like little people, because they really have all of the kind of the same parts that we do, but their skin also helps to regulate what goes in and what comes out of the cell. The outside here is hydrophilic. The inside here is hydrophobic. The next category are steroids. Steroids are a form of a lipid, and your body does produce natural steroids. Some examples, although by no means all of them, because your body produces a ton of steroids. Cholesterol is considered to be a steroid, as well as cortisol. Where have we heard the word cortisol before? When you're stressed. That's your stress hormone. When you are stressed, your body produces cortisol to help combat the physical results, and over long term can affect your ability to learn new stuff. You can also do things like overproduce stomach acids. So steroids, they are hydrophobic, meaning they repel water, and those are just a couple of examples. We're just scratching the surface. I'm not requiring you know a whole lot about steroids. When you guys get into probably a little bit in canine feline next semester, you're going to learn about some diseases associated with the steroids. And when you get into pharmacology, you're going to learn a lot about the classification of drugs that we use to help replenish these steroids if we are deficient in any of them. But for right now, it's just a classification of a fat. Finally, we have our eicosanoids. Now, I know there's some $10 words up here. Prostaglandins, thromboxane, leukotrienes. I am not going to test you over what each of these do. This is just basically so you've seen it, you've heard it, and next time you hear it, your brain will jog a memory. What these eicosanoids do is they have this very distinct hairpin or a bobby pin structure. And they do a whole variety of different jobs in the body. Some of these eicosanoids help to naturally take down inflammation. It's your body's own little version of Advil. Takes down inflammation. Some of these eicosanoids help to make you clot. That's what your platelets help with. Help you clot. Platelets are like those Spider-Man cells. And then the leukotrienes aid in bronchial constriction. So it's going to make the bronchioles in your lungs smaller, and it's going to increase mucus production. Usually that's going to happen if you have a foreign invader in there that we're trying to prevent from getting everywhere. You constrict the bronchioles so that the pathway is much smaller, and you produce a lot of mucus, because what that does is I'm now like this foreign invader, and I'm like, I'm in the lung tissue. Suddenly the bronchioles are getting smaller and smaller, and I'm like, I can't get through. And then what happens is this wave of mucus, and I'm like, and I'm stuck. And then what do? And I cough up the mucus with the little foreign invader stuck, and then I swallow it, and my stomach acid dissolves him and kills him. Isn't that what?
Isn't there like a movie that shows that? Yeah.
Is that it? I don't know. I've not seen that one.
Yeah, like
they like battle and like.
yeah, they battle in the nose because it's like yeah, and the nose is like there's police officers that are trying to control the. It's like their own little thing. It's pretty fun.
I'll have to watch that. That sounds adorable.
It does. They have like their own little characters and stuff, and mucus and all that. The good stuff. What is his name? Bill Murray.
Oh my God, I love him. Huge Bill Murray fan. Love him. But yeah, so in this case, the leukotrienes are what are initiating that response. Now, you have other mucus responses, like in your sinuses, right? Your nose drips when you have allergies. You have just in your mouth mucus, everywhere mucus. But in this particular case, we're specifically referring to the lungs because of these leukotrienes, which are a hairpin version of the fat. It's really very amazing how your body launches attacks against stuff. And unfortunately, the symptoms that you have, fever, cough, headache, stuffy nose, runny nose, postnasal drip, all of that has nothing to do with the foreign invader. It all has to do with your body's response to the foreign invader. Your body gets hot because bacteria and viruses have a sweet spot as far as temperature. And if I can raise or lower the temperature, it's no longer a good environment for that bacteria or virus to replicate or proliferate. That's why your body gets a fever.
So I've heard that like, and I'm not talking about when your fever is like really dangerous or something, but when you have like a mild fever, it's good not to take something that lowers the fever because that's your body fighting it off.
Yeah, as long as you're not in danger of brain damage, you really should not be taking anything to lower it, because that's your body's own defense systems working for you. Your body is raising your temperature to combat whatever it is inside of you. And then what happens is you have, in my mind, you guys know I'm insanely visual. I think in pictures. So now you have all of your little warriors and all of your military in your body, and they're like, crank up the heat. And they're cranking up the heat, and they're battling, and they're winning, and they're doing great, and everything is just huzzah. And then you take an Advil or a Tylenol, and suddenly just see this temperature gauge start to slowly drop. And they all are just standing there like, come on. And they're all very irritated with you now because you've undone everything that they just did.
Yeah,
So-
they show that in the movie too.
Yeah, oh my God, I could have written Osmosis Jones apparently.
Everybody watch everything is in, that's what they're doing. It was like a fever, and it was like the bad guy. He was coming in, and they were trying to fight him off. But then the guy took a pill, and then the pill came down, and he was fighting them too.
Yeah.
Bill Murray, a good guy or bad guy?
The good guy. The police officer.
I'm gonna have
And
to
they have
watch
like
that.
the little town, and it's so cute.
Aw.
I'm gonna have to watch that because it sounds like I literally
Yeah.
could have written.
Yeah.
Yeah, that shows you like not to be eating stuff off the floor.
Oh. But
Rural
it's for
and
adults, because Bill Murray's in it, right? He's like the
They
boss.
showed it in school too.
Oh, okay.
And that's the first time.
I'm gonna have to watch that. I'm gonna do that this weekend. I'm gonna try and do that this weekend.
Yeah, it's really cute. Okay.
Is it on Netflix?
And
No.
it's like, I think on YouTube. So I think it's old.
Oh, I'm sure.
It's old.
I'm sure I can find it
Not
somewhere.
that old. Like, somewhat. Not that old.
All right.
Real life and this animation. So there's
So-
like kids in the body and then outside.
So the next organic molecule are proteins. And proteins are the most abundant molecule in your body. When we think of protein, oftentimes we just think of our muscles, right? Our muscles are made of protein. And in fact, when you eat that steak, when you eat the ribs, when you eat meat, traditionally what you are eating is skeletal muscle from the animal. These proteins, though, also make up like almost everything else in your body, including your DNA. The building blocks, the Legos of proteins, are known as amino acids. So as we know, and these proteins are the most complex of all of our organic molecules. So tell me, I give you a big, huge bucket of Legos, what could you build? Literally anything. So when I have that protein, I eat that chicken Chipotle burrito. I love Chipotle. You eat that chicken Chipotle burrito, and that chicken is a protein. I think I'm not telling you any shocking information at this point. But that protein is made of Legos, and those Legos represent the amino acids. And there are a bunch. There's like 20 different types of amino acids. So in my mind, every amino acid is a different color or a different shape or a different size of Lego. The higher the quality the protein, the more colors, shapes, and sizes of Legos. I have just used all of the Legos. Low quality, like McDonald's hamburger, only uses, you know those two little brick Legos that are so stupid, and they're usually red, and the only thing, no, invisible bug. The only thing you can do is make them into the fireplace or the chimney on your house that you're making. And then when you're trying to pull them apart, oh my God, you're gonna break every fingernail you have. That's McDonald's hamburgers. There's not a lot of diversity. They're super hard to break apart, and I really can't use them very well. When I break them apart, these proteins, these Legos, can reassemble into pretty much anything in your body. They can assemble into muscle. They can assemble into cellular material. They can assemble into just free amino acids just running around looking for a job to do. They can be repackaged into anything, just like Legos. Proteins are made primarily of our four main major, wow. Thank you. Wow, you could hear Doug fall off the wheel on that one. Our four major elements, primarily nitrogen. There's a lot of nitrogen in protein, and the lower the quality of the protein, the more nitrogen we have. That'll be important next term. So protein's made of amino acids, and those amino acids can be restructured into really just an incomprehensible number of things in your body. We'll be talking, again, next term I keep talking about nutrition because I'm super excited to teach you guys nutrition. But we'll be talking a lot more about these proteins, and we'll be going into the individual amino acids and what do they do and what kind of structures can they build. That your dog is adorable. Super cute. I thought it was a stuffed animal you were holding for a minute until it moved.
He will be one day.
Oh. Hey.
I don't want to let him go. I've had him for 11 years. He's my baby.
Aw. He's very cute. All right, so I am not going to quiz you over. You don't have to memorize this huge list of amino acids. You are welcome. These, just so you've seen them, so you're kind of aware of what they are. These are the amino acids that we'll be going over next term. And I can take, so each one of these is a single Lego. Every one of these is one Lego, and every single one is a different color or a different shape. No two are the same Lego. And so I can take these Legos and I can pull them out and I can rebuild other stuff with them. I think there's probably only one on here that you all have heard of, tryptophan. How do you know about tryptophan as amino acid? It's in turkey. Well, you know what? I'm going to clear up something right now because I feel bad for tryptophan. I need to be an advocate for him right now. Because when you eat the turkey and then you go onto the couch and you go into your coma, I don't know what you people do. I sit and watch football. I'm a huge football fan. So I sit and watch the game. I don't know what you guys do. I can't even fathom. But as my body is breaking down that protein, that turkey, there is a lot of tryptophan in turkey. And then we say, oh, it's the tryptophan that has made me sleepy. Because once you get settled on that couch, right, the only thing you can do is reach over and get more pie. I usually keep it right there within arm's distance. Because then you're just shoveling stuff in your cake hole. Oh, I do love Thanksgiving. But let me tell you right now, it's not tryptophan's fault. You've been blaming him needlessly, and it has got to stop. It is not tryptophan's fault. Does tryptophan have sedative properties? Yup. But in order for it to make you sleepy, it's the only amino acid you can take in, and cooking degrades it to the point where it will no longer have those sedative properties. So quit blaming tryptophan. It's because you ate too much, you gluttonized yourself, and your body is like, okay, we can't get into trouble right now because we got to use all this energy for digestion. Your body your brain looks around and goes, this is a safe space. You just go to sleep and maybe don't go anywhere. You just go to sleep. And that's exactly what happens, is your heart slows, your arms feel heavy, you're just laying there watching the football, and you let all the energy go towards digesting this massive meal you just ate. So quit blaming tryptophan because we've had enough. We're not taking it anymore. So the structure of proteins, like I said, you can build anything with Legos. You can build any shape, any size. And it's the shape and the size and the type of Legos that we use that determines its function. Again, Legos are a perfect analogy for all of these components. Depending on what I use my Legos to build, that determines its function. If I use the Legos to build a car, I'm going to play with the car. If I use them to build a house, I'm going to play with the house. It's the same thing in our body. I can build anything with them. One of the specific structures that I can do with proteins is really interesting. We have these things called antibodies, and antibodies, I love kind of hinging this abstract note kind of boring lecture, because I do know this stuff is dry, guys, I get it. But hinging it to something that's happening in our own lives today. The word antibody has certainly been in the news. Because what an antibody is, so now you're going to know, when now you hear, oh, we need to have antibodies. When you get infected with something, your body has these little private investigators walking around with a wanted poster. And that little private investigator, he's only got one wanted poster for one foreign invader. When he sees he's like, oh my God, that's him, it's him. He lights a big beacon, and Immunity Group sees the beacon, pulls the flashcard for that particular foreign invader, and he knows exactly step by step, ABC, what to do to defeat it. The problem is if you have a foreign invader that your body's never seen before. I don't have a private investigator. And so now I have this foreign invader just like walking around, cock of the walk, burn, my new digs. And the military, well, first off, it might take a while for Immunity Group to even realize he's there. Now he's amassed an army. So now instead of one foreign invader, I have an entire army that I wasn't even aware of. And Immunity Group goes, oh my God, stranger danger, stranger danger. Send in the military, but he doesn't know exactly what steps to take. And so the military, which are your white blood cells, come in and they start battle. And now Immunity Group is taking notes and he's sketching it out, making his wanted poster. Now I have a private investigator I can give that poster to. Now if you get infected, theoretically, if you get infected again, doesn't mean you're never going to get infected, but it does mean your body knows how to fight it off. And you're not going to have the same severity of illness, and it's not going to last as long. A wonderful example, and no, I am not going to say the C word. A wonderful example of this is, well, actually, technically, damn it, Doug. Technically, it is the C word, chickenpox. I'm just having a day today, guys. We're just having a day. Chickenpox. I'm assuming everyone in here has had chickenpox at some point in their life. You have not? Oh, no. No, wait, what? Wait, okay, how many of you have had chickenpox? OMG.
I think that they came up with the vaccine and people have stopped getting it nowadays, but the people who were born before a certain year have had it.
I was born 99.
Because I was born in 91.
94 for 96. I was born a little bit before that. Shut up. Stop laughing. I did not ask for your judgment. I said a little bit before that. I hate you all. You know what? I'm going to end class and poo-poo on all of you. Now you've hurt my feelings. I only have one. All right, so yeah, back in the day, they had chickenpox parties. One kid on the street would get it, and they would make us do a play date, so everybody else on the street would get it. Yeah. Unlike the virus we're dealing with today, however, chickenpox, it's best for you to get it when you're young, because it can be quite devastating if you get it as an adult. And so, but what happens after you've had chickenpox, now you never get the same version of chickenpox again. Now, can the virus still activate within your body? Yes. Does anyone know what happens to you if the chickenpox virus activates in your body? Shingles.
Shingles.
But it's not the same reaction as the chickenpox.
My grandma just got it like 2 weeks ago.
Oh my God, my mother gets terrible, terrible shingles. I feel so bad for her. So what happens is now my immunity, here's the sneaky thing. I know we've gotten off of this organic molecules, but this is waking you guys up a little bit because I think it's pretty cool, pretty fascinating. All right, so I've had the chickenpox. And I have my private investigator with the chickenpox wanted poster for the virus. The problem is that virus went and got some plastic surgery. So now the original chickenpox virus, he comes walking in, and PI goes, hey, stranger danger, bam. We know exactly how to get rid of them. So you don't get the symptoms. We get rid of it so fast you don't even have any symptoms. The problem is that the virus with the facelift, it's the same virus, but he doesn't match the wanted poster. He's allowed to come in, hello, private investigator man, and off he goes. I don't know why he's walking like this. He's very, very determined. But because he had the facelift, the reaction to him is a little bit different. Now your immunity group goes stranger danger, sends in the troops, but it's similar. You get the blisters, but the thing is it's just slightly different because the virus has gone in and changed the way he looks. And that's the big tricky trick with viruses, is that they can alter themselves in a heartbeat. The minute that I find a drug that kills them off, they go and they change themselves so the drug doesn't work anymore. Or the minute that I have a private investigator, I get the vaccine, tricks my body into creating a private investigator. Suddenly he doesn't look like the wanted poster anymore. And so these viruses can change and they can evolve like that. And so that's kind of a little bit about what's going on in the news right now. The structure of these proteins being your antibodies. So now you know when you're hearing all these words in the news, now you're actually part of the educated.
I have a question. So, except for you, Anna, did y'all think of the chickenpox as like the bubonic plague or something? Like it just happened way back in the day? She was like, yeah.
Yeah, I never heard of it. I never got it.
Wow.
Yeah, I mean, it wasn't that far back because like, probably its heyday was probably in the 70s and 80s.
I mean, I know it's still exists.
Yeah. All right, so these proteins have very specific structures. This is all we're talking about here is how did I reassemble the Legos? I have a primary structure, which is exactly what it sounds like. This is the amino acids linking together, creating a shape. And that shape determines the job that it's going to do within your body. The secondary structures, so now I've taken these Legos and I've put them into a chain. And now I'm going to go ahead and start bending the chain. These are flexible Legos, by the way. I'm going to start bending the chain and I'm going to put it into a specific shape. Because again, it's the shape of the Legos that will determine what my body's going to do with it. Once I have these natural bends, now I'm going to start doing the detail shaping. This is called tertiary. It's also known kind of as a secondary. Once I get the natural bends, now I can go in with like origami and I can start folding it and really getting an intricate shape. Quaternary is where I have two of these structures and I bond them together. So again, the primary structure is where I take Lego, okay, I need this Lego and I need a blue Lego and I need a 2 Lego and I need a green Lego, and I make the chain. Secondary is where I allow it to have its natural bends. Tertiary is when I start doing origami, making it a very specific shape. Quaternary is where I take two of those origamis and I smoosh them together. So right now, all we're looking at is the definitions of these terms. Is everybody okay with that? It is.
Like the pyramid.
Absolutely. This is in fact science. This is science that I'm throwing at you right now. For my little visual learners, primary. Every one of these little dots is an amino acid, and you can see I've assembled them into a single line. Secondary, I allow it to start following the natural bends. Tertiary, I start doing origami folds, folding it into a specific shape. Quaternary, I take two origamis and I bind them together. This is just a link to a YouTube video that I have. It's also on my website that goes over all of these different organic molecules. All right, still moving on to the different types, the different categories of these molecules. I have structural proteins, which are exactly what they sound like. They form a structure, they're rigid, they are stable. They're basically just the scaffolding. They're the joint studs in your house. They're what support everything. Some examples, collagen. Where have you heard the word collagen? What?
And face treatments.
Yeah, you get the collagen in your skin. What collagen is the elasticity. So unfortunately, as you grow older, gravity works. Gravity's working right now. But what it also means is gravity is constantly pulling on you down. And it is this constant pull that can cause the elasticity to go out in the underlying tissue, which is what gives you wrinkles. And then you put the cream on or you get the injections and you tighten everything up. Keratin. I know you guys have heard the word keratin. Everybody, you can use keratin treatments on your hair. Not doing exactly what you think it's doing, but that's a story for another day. But yeah, keratin is what gives these specialized, it's what gives the strength to your fingernails. It's what gives your hair the look. And then finally, we have a very specific structural protein called actin and myosin. When we get into the muscular layer, this is going to be very important. Actin and myosin are these protein filaments, and they kind of interlock with each other like this. And these are the filaments found in your muscles, your skeletal muscles, and your smooth muscles, but we'll talk about skeletal. So they're like this, they're kind of just overlapping. And then a message comes from your brain that says, hey, we want this muscle to contract. And then these two filaments ratchet over each other like this, and the muscle contracts towards the middle. So I have actin and myosin here, actin and myosin here, and when they interact, it causes my muscle to contract, which causes a movement in the limb. So there you go. Give you guys a minute.
Can y'all see her?
I'm hiding from you. That's fine. See, it goes away. Yeah, I snuck over here and then I was super quiet so the owl couldn't find me. It's my own private little game of hide and seek. See, now it found me. That. It's the little things, guys. It's the little things, and sometimes it's just for me. And that's okay. And look, now he's like, where did she go? I can hear her. I can see her. It's a game that I now play in my own brain. All right. So some functions of proteins, guys. This is a review slide. This is just putting into one slide everything that we just talked about. I like to put in these little review slides because it consolidates information. The last like 5 or 6 slides we just talked about, the majority of that information is here. So when I mentioned that I've put in a review slide, you can put a little star beside it because a lot of the information you would need as far as testable material would be found on this specific slide. Not the only place, but this is a good slide. If you can remember stuff on this slide, you would do okay. Some of the functions of our proteins, we already talked about hormones. We talked about antibodies. You have your protein-based hormones with different shapes. The shape denotes the job. And then enzymes. And what enzymes are a form of a catalyst. Who remembers what a catalyst is? Yeah, it starts some sort of reaction. Those are a function of proteins. We just talked about all of those in pretty great detail. So these enzymes, they speed up our chemical reaction. A lot of them end with the suffix ase, A-S-E, amylase, lipase. 2 examples, those are digestive enzymes. And they have, they catalyze, they initiate, they speed up some sort of reaction. So they're very, very much like a catalyst. That's it. That's all you need to know about that. Acetylcholine esterase. I'll give you guys a minute. Oh, found me. All right, do I have any comments, questions, concerns so far? Is everybody okay? Picture. So here we have a protein. Here we have a receptor, which is like a lock and a key. And when I have that enzyme come in, it initiates some sort of reaction. Finally, our nucleic acids, this is what makes up your DNA. You have 4 nucleic acids that make up DNA. These molecules, these nucleic acids, what was I about to say about that? Oh, the 4, you don't have to write it down, but just so you've heard it in the next chapter, adenine, guanine, thymine, and cytosine are the 4 nucleic acids that make up your DNA. Adenine and thymine bind together. Cytosine and guanine bind together. And it's the pattern, the repeats that bind together that give you your genetics. DNA is generally found in the nucleus of the cell, and it is unfathomably long. Everything about you is blueprinted in your DNA. And that blueprint was donated by your mom and your dad. Part of their DNA sequence from each goes to make you you. And part of their DNA sequence came from their mom and dad and their mom and dad. And that's why you might have a child who is the spitting image of a great grandparent, because it just so happened that your repeats very closely matched their repeats, because that is how genetics work. When you were born, it was already determined what color were your eyes going to be, what color was your hair going to be, how tall were you going to grow. You're this big when you're born, your body already knew exactly how tall you were going to grow. How big are your feet? What size shoes are you going to have to wear when you're an adult? All of that was pre-mapped out for you. I find that really fascinating. The other really cool thing about DNA is it's not just found in the nucleus, it's also found in, we probably all have heard about this, the powerhouse of the cell, the mitochondria. Mitochondria is a remnant of evolution, a really fascinating remnant of evolution. The mitochondria, and I won't go into too much detail, I think it's cool. The mitochondria was an entity unto itself. It was what we call prokaryote, which is a single cell, no nucleus. And he just kind of existed on his own. When these complex cells started to evolve, they needed more energy than what they could provide. And so basically, again, cartoon in my head, basically what happened is this poor little complex cell is super struggling, and he's just like, I don't have the energy to be me. Mitochondria is over here, and he's pretty at risk. I mean, he's just open to the environment. Mitochondria goes, hey, friend, hey, guess what? I have all the energy, I have energy to spare. So I'll tell you what, if we incorporate and work together, you give me a safe space, I'll give you my energy. And complex cell was like, okay. And they merged together, and that's exactly what happened, a nice symbiotic relationship. The complex cell now had the energy it needed. Mitochondria had a lovely safe space. Not only that, but mitochondria, if the cell is like, we need more energy, mitochondria can go and make another one. And now you got two that are making energy. And if the cell's like, there's still not enough power, and now you have more mitochondria that are all producing energy. And so it's this truly symbiotic relationship that is really beautiful, beautiful example of how these cells evolved into what we are today. Half of DNA sending a message around your body, that's gonna be RNA. When I take this DNA and I go, and I unzip it, I can take half of this and I can send it all over the body, and my body can then reassemble the DNA perfectly, because certain nucleotides only connect with other nucleotides. So that's the story of DNA and RNA. And all of that, still proteins. Whew. Well, my acting abilities are taking it out of me today. So this is just a little bit, kind of a review. Nucleotides, I'm not going to test you on this. They are made of a sugar and a protein, and they're named for their nitrogen base. That's it. And there's their structure. I'm not going to make you reproduce their structures, just so you've seen it. Finally, here we have the nucleotides: adenine, guanine, cytosine, and thymine. These four are all found in DNA. These three are found in RNA. And then the thymine is replaced with this guy, uracil, in RNA. I do want you to put a little star beside this slide, because I am going to test you over which of these nucleotides are in DNA and which of these nucleotides are only found in RNA. The other thing is we have in DNA specific nucleotides binding with only one. Adenine will only ever bind with thiamine. Cytosine will only ever bind with guanine. How do I remember that? Apple tree, put your car in the garage. Adenine and thymine, apple tree. Cytosine, guanine, put your car in the garage. So now you can see if I have half of a DNA. So this right here, technically that would be a U, but you get the idea. So this is half. This is a message that I'm sending throughout the body because I need to build a new DNA. Can I rebuild a perfect, exact replica of the original DNA from this? So what binds with A? What binds with T? What binds with G? There's another C. What binds with A? T, C, G. So by only having half and knowing that nucleotides only bind with one other nucleotide, I can make an exact replication of that DNA. You guys just built DNA, that's pretty cool. All right, we are gonna pick it up here because time flies when we are having fun. Stop. We are going to pick it up here on tomorrow, and then we're going to get started on the next chapter where we are actively going to start looking at cells. We're going to look at the phospholipid bilayer. We're going to look at the cytoskeleton. We're going to start looking at what goes in and what comes out. And we're going to look at the organelles, which are the little organs inside the cell that keeps it alive. They have cells very similar to our brain, our kidneys, our liver, etc. And so we'll go ahead and look at those. So that's the evil plan for tomorrow. Do I have any comments, questions, or concerns?
What are the test yourself questions due?
They will be due next week sometime. I've decided that I'm not giving you a test over the weekend. And so I will announce it. It'll probably be maybe Tuesday. Yeah, probably be like maybe Tuesday. That's what I'm anticipating. Oh, we did have some football fans in TV land. Let me look. Oh, Lord. Ugh, Ashley, you're a Cowgirls fan. Ugh. Heck no. All right, so I need to mark Annette. Ugh, Cowboys. Cowboys are terrible. All right. Annette, I will mark you present. All right, you in TV land, I'll see you guys tomorrow. And you guys, I'll see you tomorrow too.